Hello everyone and welcome to a series of lectures on chemistry in everyday life. In this series of lectures, we are going to study drugs and their function, certain classification of drugs and their mechanism of action. When we will discuss mechanism of action of drugs, we will discuss receptors, we will discuss enzymes as drug targets. Later on, we will discuss certain diseases and the drugs which are useful to alleviate the disease symptoms, which would be antibiotics, anti-inflammatory drugs, antipsychotic drugs and anti-fertility drugs. Towards the fag end of this series of lectures, we will be studying artificial sweetening agents and food preservatives, and then finally we will conclude this series of lectures with chemistry of cleansing agents. We will now begin with the series of lectures. What is chemistry? Whenever you think of chemistry, what comes to your mind? Well, when I think of chemistry, what comes to my mind is this. We think of certain making of bonds, certain breaking of bonds, and that is what we think when we think of chemistry, right? Basically, chemistry is nothing but a glorified cooking, right? So, I always call a person dealing in organic chemistry as a glorified chef. So, what we actually do? It is organic chemistry or chemistry per se is a very vast subject. You find implications of chemistry in almost everywhere, be it medicines, be it energy, be it natural products or catalysis, or then chemical biology, or you traverse environment. There is not a single sphere which you would come across in a discipline of science which would not involve chemistry. It is that important. We do not really need to venture into so sophisticated fields of chemical biology or asymmetric catalysis. Chemistry is very much here, just around us all the time. And I will give a couple of examples to prove how we use chemistry in our daily lives, day in and day out. For example, somebody cutting an onion and tears rolling down his eyes. You know the reason, and the reason is nothing but organic chemistry. There is this compound which is called propanethiol S oxide, which emanates out when you cut onions. So, when onion is mixed with certain enzymes, it emanates sulfur gas, and the gas gets to our eyes, which creates certain mild acids, and that irritates the eyes. So, it is organic chemistry working well into our eyes, right. What we do early in the morning, take a cup of coffee and get a feeling of waken up, right. So, what gets this feeling of freshness, energy and wakefulness when we take a cup of coffee? It is again organic chemistry. The molecule which is behind all these feelings is a simple organic chemical compound called caffeine. Again, organic chemistry into our daily lives. Or then when you get ready to come to your office or come to your schools, one would not forget to have a spray of perfume. What is it which is giving such a fragrance when you use perfumes? Again, chemical, organic chemical small molecules called esters, right. So, the point I am trying to make with all of this is you find chemistry in all the spheres, in something which is very close to you every day, right from the beginning till the fag end of the day. For this lecture and the coming couple of more lectures, what we are going to concentrate is medicines, and the role which organic chemistry plays in the domain of medicines, right. So, basically we are going to discuss in today's lecture and another couple of lectures is chemistry of drugs. So, let us begin the topic. In today's lecture, what I have planned for you is we will discuss drugs versus medicines and whether these two terms are synonymous. Then we will move on to classification of drugs. Later on, we will figure out how one can name the drugs, right. And then we will move on to drug selectivity in body, which means if you have taken a drug for a particular pathological symptom, it should be able to alleviate only that particular symptom. Finally, we will learn about finding of a lead compound. What is a lead compound and how an organic chemist or a medicinal chemist goes about it. And then later on, what do we do with that lead compound, and this we will study under an heading of molecular modifications. So, that is very much up for us for today's lecture. Let us begin. When you go to a pharmacist and somebody in the family might be running a high fever, what do you ask? Do you ask for a medicine or do you ask for a drug? Or whether it is immaterial, if you ask for a drug or a medicine, it is the same thing. Let us try to understand these two things in a larger perspective. Let us see what we mean by the first thing here on the left hand side, which is drug. Drug, by its definition, is any chemical compound which brings about a physiological action in the body, right. And then an activity of the drug is its pharmacological effect on the subject, that be human beings or animals. So, by this definition, if I am to simplify it even further, anything which we take and which brings about an effect, any change in the body would be termed as a drug, right. Which means whatever we take, all the drugs which we consider are drugs, are all these good, or can these also be bad? So, if we consider that all the drugs are good, then what do we think about drugs like cocaine or drugs like heroin? Or if not that, what about somebody taking, let us say, 6 pills at a time of aspirin rather than advised dose of one small pill, which we can study under an effect of overdosing. So, what do we consider all these drugs now? Drugs which have been overdosed, drugs like cocaine or drugs like heroin, which are psychoactive drugs. Now, to understand this and to relate it with the concept of a drug as we understood as any substance which is there to bring about an impact in the body, I will give you an example of heroin. Let us just introspect it. In the year 1898, when this drug was actually marketed, and this was marketed because people believed it has much better analgesic properties in comparison to its predecessor, which was morphine. So, it was really marketed and brought to the market with a lot of fanfare when people said, it has those kind of heroic abilities. And trust me or not, the word heroin is derived actually from the word hero. Somebody would have done something gallantry efforts. So, that was the impact and that was the reputation of that drug once it was brought in the market in the year 1898. Just 5 years down the line and we reach to the year 1903, when most of the countries, they had to ban this drug overnight. And this was done when people realized that in addition to its analgesic effects, this drug has also very bad addictive properties. So much so that it can become lethal to most of the people who become addicts to this drug, which was heroin. So, in one shot, one which was hailed as a hero was decimated as a villain. The drug did not change, the molecular that did not change, right. Another example. So, this example I also gave in the previous slide. Every day in the morning, when you feel that kind of laziness, you go to the kitchen and prepare a cup of coffee, because it gives you that feeling of wakefulness, right. But have you seen some people which have more or less become addictive to coffee? You must have, right? People who would take just 10-15 cups of coffee in a day. So, again, it is the same molecule I told you, that caffeine, which had good properties, people consider them good properties, but then it turned into a villain again. So, it made the person addictive to it, right. When I discussed in the previous examples something which was heroic in the beginning and it turned into a villainous, I might now propound another example in which just the opposite happened. Look at this large molecule on your screens, which is tuberculin. This molecule has been found in in the native tribes of Southern America. And why those tribal people used to what they would use with this molecule was, they would take this molecule and put this molecule on the tips of their arrows, and then they would during fights they would throw these or hit people with these arrows which were impregnated with this compound, and then this compound is lethal in certain amounts, right. So, the person would die. So, this was a very toxic poisonous compound. Now, somewhere down the line, scientists realized that this compound under controlled doses can actually be a boon, since this compound is a very good relaxant. Hence, this compound is now used, can be used in surgical operations to relax muscles. So, here is an example where a compound which had a villainous trait has been converted into a hero down the line. So, the point I am trying to make is that every drug which we just saw is a molecule which is going to have an impact on the body. That impact could be positive or that impact could be negative. So, any molecule or any drug which would have a positive action or a positive impact should be called a medicine. So, when you go to a pharmacist and ask for a drug, you are actually asking for one such drug which has a proven track record of positive action. So, it has turned into medicine, right. So, if this is what we see, then we must also define what is a medicine. So, then a medicine is a chemical which is intended to use in the diagnosis, cure, mitigation, treatment or prevention of disease in man or other animals. So, look at all the traits, and all the traits are positive here. We did not say any of these things when we defined a drug. So, we can say medicine is a subgroup of a larger group of drugs, all right. So, we can also conclude by saying that every medicine should be a drug by virtue, but every drug need not be a medicine, right. So, what we saw about medicine? We saw about medicine that a molecule which could be used in diagnosis, which could be used in prevention, or which could be used in treatment of a pathological condition, right. So, a drug molecule which is used in diagnosis, and you might be aware of certain examples, a person going under magnetic resonance imaging or MRI is given certain chemicals, right. So, that is MRI is good. So, that would be a diagnostic medicine. Well, let me reiterate here that for the rest of the discussion, I will be indiscriminately using the term drug or a medicine, and you might be able to just judge or use it for the purpose, whether it is for the good purpose or a bad purpose, right. Likewise, for prevention, the example which comes to my mind are those vaccination shots, right, which are given to infants to prevent them from having dreaded diseases like polio and other dreaded diseases in the later on in their lives. And for treatment, where actually most of the molecules come into picture. So, it is when a person actually is infected with a particular disease. So, then there are the there are those molecules which we call medicines, which are there to alleviate and treat the person, right. So, this basically compiles the difference between a medicine and a drug for us. In a nutshell, we can say that a drug can refer to any substance which would have an impact on the body, and that impact can be positive, that impact can be negative, that impact can be intentional, or it can be even a side effect, right. So, need not be a positive impact all the time, whereas a medicine is a substance which is designed to prevent or treat a disease. So, it has got to have a positive impact, right. So, with this we will move on to the next topic of today's lecture, and which is about classification of drugs. How do we classify the drugs available before us or before a medicinal chemist? So, drugs are basically classified on the basis of their pharmacological effects. They are also classified on the basis of chemical structures. They are also classified on the basis of drug targets, or finally, they are also classified on the basis of site of action. Let us try and understand these terms in a little bit of more detail. So, let us try to understand classification of drugs in terms of their pharmacological effect. What do I mean when I say pharmacological effect? You might have seen people saying analgesics for pain killing effect, right. So, if somebody is having a lot of pain, people will say, have you taken any analgesics, right. So, when we say analgesics, we do not refer to any single molecule. We refer to a spectrum of molecules, and all those molecules are supposed to bring about the same impact, and that impact is to alleviate symptoms of pain. So, they must bring down pain in a sufferer or in a patient, right. So, then this type of classification, which is based upon the effect, the pharmacological effect, is something which we categorize under this head, which is classification based upon pharmacological effect. So, under this head, the drugs which we would name would give information about a particular type of problem. For example, analgesics. So, you would understand the moment I say analgesics, you would understand I am talking about a pain killing drug, or if I say antiseptics, you would immediately understand that the molecule I am talking about is going to arrest the growth of microorganisms, right. This type of classification is actually very handy for doctors and physicians, because it gives them an idea about a wide range of drugs available for a particular pathological condition. For a medicinal chemist, though, it has a limitation, and it has a basic limitation in the fact that two very different drug molecules can actually bind to bring about the same impact. So, analgesics, what I mean to say is there could be two very different analgesics, or for example, there could be some analgesics which might also behave as an antiseptic, right. So, if this happens, there is a problem in front of a medicinal chemist how to categorize it, whether call it an antiseptic or you call it an analgesic. So, there are several other examples also. I am not going to spend time on other examples. I will move on to the next system of classification. I hope this system of classification is clear to everybody's mind. The second system of classification of drugs is based upon the chemical structure of the drug or chemical structure of the molecule, right. So, then it is based upon an assumption that for a particular therapeutic or a particular disease, all the molecules or most of the molecules which are useful to alleviate symptoms of that particular disease should have more or less similar structural features, right. For example, look at this molecule here. This is an example of sulfonamide, right, and sulfonamide, as some of you might know, have been those one of those broad spectrum antibiotics which were among the first generation of antibiotics, the first ones to arrive in the arena of drug discovery, right. So, if you look at sulfonamides, you would categorize sulfonamides with these structural features. In most of the cases, you would have this sulfonylamide group. Then it would be also having an aromatic structure which might be joined with an amine here, right. So, this corresponds to a structure which you would call a sulfonamide, and then most of the molecules having this kind of a structure would be supposed to act as antibiotics, right. But again, there is a limitation, and almost of the same kind as we discussed in the previous classification system. Now, sometimes you have two very similar molecules which would have quite a different action. For example, steroids. You have steroids almost similar in structures, they have those steroidal backbone which would have been used for various therapeutic impacts. Okay. So, then again this system of classification, although it is simpler, but it does not solve the purpose of a medicinal chemist. Let us move on to the third one here in line. The third one of classification of drug falls on the basic sense that where your drug is going to act, which particular biological process is being influenced by the action of drugs. For example, I can call some drug antihistamine. When I call some drug antihistamine, what do I mean? I mean that it is going to arrest the action which a class of biochemicals called histamine bring about, right. So, histamines are known to bring about certain symptoms of inflammation, right. Then if I talk about antihistamines, I am certainly talking about molecules which are going to alleviate symptoms of inflammation. So, that makes much more sense to me. So, then this system of classification is certainly advanced over the previous two systems of classification we studied, though it also is impregnated with a similar limitation that in certain cases a similar target or a similar biological process would have two different therapeutic impacts. For example, antihistamines can be of two kinds. One type of antihistamines are able to bring down or alleviate symptoms of diseases such as hay fever or other allergic reactions occurring in the body, right. Such as somebody is very allergic to pollens. So, then they develop these symptoms of repetitive sneezing and running nose and all that. So, they are treated with those antihistamines. Likewise, there is another class of antihistamines which are not treated, which are not administered to treat any of these symptoms I just mentioned. In fact, they are administered to treat disease like peptic ulcer, right, and peptic ulcer and hay fever are two completely unrelated pathological symptoms. So, then again this system is also not a foolproof system of classification of drugs. This brings me to the last one of classification of drugs, which is based upon the site of action. What do I mean by site of action? With site of action, I mean that for every drug to act and to alleviate symptoms of a disease, it needs to find that one particular point, that one particular epicenter in the body which is actually responsible for the release of that drug, or which is responsible for the genesis of that disease, right? Which means that every disease is more or less, with some exceptions also, but then most of the diseases, they are emanated, they are arising because of some aberration at one particular point or one particular molecule or one type of molecule in the body. So then your drug has to target that particular epicenter in the body, and those epicenters are generally biomolecules, and those biomolecules are actually called drug targets. So the most common drug targets are generally carbohydrates, they can be lipids, they can be proteins, or they can be nucleic acids. Drugs which have similar structural features may have similar mechanism of action on those drugs. So this type of classification is based upon the type of molecular target which is being hit by that particular drug, and then this is more or less like a foolproof mechanism of classification. For example, if I say if I call a drug as COX-2 inhibitor, I mean that that particular molecule is going to target an enzyme called cyclooxygenase 2, and this enzyme is responsible for the symptoms of pain. So then any anti-inflammatory, pain relieving properties would be emanated by molecules which are going to act or react or target this particular enzyme, which is COX-2, right? So any drug, any structure, if I call it COX-2, people would realize what it is going to bring about as a therapeutic impact. Then the third thing about drug is you have got to know how to classify the drugs. The second thing is how to name a drug. Now naming is something tricky, right? Why it is tricky? Because most of the chemists, they use chemical names which explain the structure of a compound, like some of the structures we just saw in the previous slides. But then those structures cannot be given as the name of the drug molecule, simply because they are too complicated and too long for physicians or for the general public. For example, I talked about sulfonamide in I think 2 slides previous to the last slide. Now if I had to give its chemical name, I would call it like 4-amino benzyl sulfonamide compound. Now this has been stretched. It might be good for me, it might be easy for me as an organic chemist, but it might not be it might not be an easy job for, let's say, a physician sitting in a clinic to remember that name. And that is why it's important we name the drugs as simple as possible. Now it means that any discoverer can use a name whatever to its choosing for that particular molecule. This is right, this is correct to an extent. Now what happens if I have discovered a molecule? I'll file a patent for it, and for another 20 years I can use that molecule, I can only sell that molecule with whatever name I like. And when a molecule is discovered by a pharmaceutical company, they tend to pick a very simple to remember name, right? So that people can easily relate that name with that particular disease, right? So then it will be useful for them in future. Why in future? Because that patent will last for only 20 years. After 20 years, anybody can make that molecule, apart from the discoverer. Discoverer can also make, and anybody else can also make. For that reason, not everybody can use the same brand name. They can use what is called a generic name for that particular molecule, which is given by a set of experts, which given like a list of 10 compounds, 10 names they provide to the discoverer, and the discoverer has to pick one of those names. Invariably, pharmaceutical companies pick difficult generic names and easy brand names, so that 20 years down the line, when everybody is making that molecule, people would still go to a pharmacist and ask for a brand rather than a generic compound. I will give you an example with this molecule called low pressor. It is a brand name for a drug for a generic name metoprolol. It is a beta blocker, so it is used for hypertension. It brings down the blood pressure. Now, imagine somebody having a high blood pressure. Which name would he prefer? Low pressor, which is quite in sync with his high blood pressure, rather than another name which is metoprolol. So, that is the trick, and I hope all of you have understood the trick. So, that is how naming of a drug is done, right. So, there is nothing else which I need to just read from this. I think the basic sense I have given to all of you as far as naming of drugs is concerned. The next point in drug discovery or drug design is drug selectivity. When we say drug selectivity, what we mean is that if you are having pain in the body, you should take a drug. That drug should only alleviate pain in the body. It should not make you feel dizzy. It should not feel you burning sensation in your stomach. If all that is happening, it means that drug is not really a very good drug. It is impregnated with what we call as side effects. So, to alleviate side effects, this drug selectivity comes in handy. There are three factors on which this drug selectivity depends. Number one is the targets or target, right. Target, I already told you, is that particular epicenter of a disease which is responsible for the disease in the whole body. So, then your drug should only target that particular epicenter. We will learn about this target in more details in this lecture and the coming lectures. And then second is mode of administration. What do we mean by mode of administration? Have you taken a capsule or a pill? So, have you taken it orally, or have you taken, let us say, a tube, right, and you have taken it a subcutaneous, you have applied that cream. So, that cream is that particular mode of administration is subcutaneous mode of administration, or if you have taken an intravenous injection, IV injection, right. So, all these are mode of administration, and they depend, they govern what kind of selectivity a drug may impart, or the profile or the spectrum of side effects greatly. Finally, is concentration or dose. What type of dose or what type of concentration is suitable for you or me? Generally, after a lot of research and lot of work by scientists, there is a standard dose which is provided for, let us say, for adults, for old people and for children. But to tell you the truth, with the different metabolism taking place in every different person, each of us for a particular disease, for a same level of disease, would need a different amount and a different dose of a drug molecule. That is the truth. But since it is so difficult to implement, we are generally given a journal dose, which is the same for me, same for you, same for any other adult, right. The last two things I spoke about, mode of action and concentration dose, they actually fall in a class of in another term which is called pharmacokinetics. I will discuss this pharmacokinetics in the next slide. I think the time has come when I introduce a few terms before you guys, before we move on with this topic. So, I spoke about pharmacokinetics. Pharmacokinetics is nothing but the journey of a drug through a human body, which means what happens to a drug the moment that drug is administered inside till the drug is given out, the drug is eliminated, right. Every drug molecule, understand, is a foreign particle, is a foreign molecule. So, your system, your body would like to get rid of it, irrespective of whether it is bringing a positive impact or a negative impact. So, that whole journey is discussed under one head, which is called pharmacokinetics. This is beyond the syllabus purview, and I am not going to discuss pharmacokinetics here, but I wanted to bring to your notice what pharmacokinetics is. half-life of a drug. It is the time required for the concentration or amount of a drug in the body to be reduced by 1/2. What is its implication? So, every drug would have a different half-life. It means for how long will it stay in the body, how easily the body would eliminate or throw it out. It's on the basis of half-life of a drug that a physician prescribes a drug to you, as some where you have to take it just once in a day, or some drugs which you have to take every 3 hours or 4 hours, right. So, a drug's plasma half-life depends on how quickly the drug is eliminated from the plasma, it means from the blood. The other thing is pharmacophore. A pharmacophore is a part of a molecular structure that is responsible for a particular biological or a pharmacological interaction that it undergoes, which means that not whole of the molecule. I talked about sulfonamide, right, or I could talk about any other molecule as a drug, and you would understand and appreciate not whole of that molecule is actually responsible for alleviating symptoms of that disease. Just a part of it, just few functionalities are actually extremely critical to bring about the effect of that particular drug on that disease we would be discussing. That part of the molecule is called pharmacophore. And then finally is a target. I told you about a target. A target is an entity which is responsible for a pathological condition. So, it is that epicenter which is actually responsible for that particular disease and where your drug must target, right. So, this brings me to a very important aspect of drugs, which I hope all of you would enjoy with a lot of inquisity, and that is about how to make drugs, right, from where these drugs come. I can tell you most of the drugs have their origin in the folklore, in the past, in the ancestors, how our ancestors used drugs. In fact, so much so that some of the molecules which we use today as drugs, they have been used for centuries through our ancestors, or how our ancestors used them. For example, I have a couple of examples here, or 3 examples. One is foxglove, which is being used in Europe a few hundred years back, and it furnished a compound called digitoxin, which is a cardiac stimulant. Second is the bark of cinchona tree. Again, it was discovered few hundred years back in some Southern American countries, from where it was traveled to Europe through certain monks. And the molecule which is responsible turned out to be quinine for relief of malaria, and you would be surprised this molecule is still used for alleviating malarial symptoms. Likewise, willow bark, which contains salicylates, are still used in a little bit modified forms for alleviating fevers and pains, and that is acetyl salicylates, okay, the molecules which are used for alleviating fevers and pain. As a medicinal chemist, you must understand that the goal is always to make compounds which would have potent effects on the given disease with minimum side effects, right. So, if I need to cut that story short, a drug molecule must react selectively with its target and should have a minimal negative effect, which means it should be target selective. It should only react with that epicenter of a disease, right. This we also studied a couple of slides back. Now, I spoke about all that folklore knowledge and what it provided to us. It provided us a repository of certain molecules to start with, right. The molecules which we knew were efficacious, but we also knew that these molecules were not really top shelf. So, we needed to do something to these molecules to make them even more effective and more selective. Now, we call all these molecules as prototype, and these prototypes are in fact more appropriately called lead molecules, right. So, these molecules are isolated and their structures is determined, then they serve as a prototype in search of other biological active compounds. This is about when you gather all the knowledge which was previously present. What about if you just hit upon a molecule which shows certain promising effects in one particular area of disease? So, these prototypes and also such molecules which have preliminarily shown a very promising activity against a particular disease are actually called lead compounds. Okay? These are called lead compounds because these compounds have actually provided you a lead. They have provided you a clue as to what type of molecule you precisely need to find or you precisely need to make in order to reach your target selective drug or target selective goal. Okay? Now, for that end, what a medicinal chemist generally tries to do is they try to bring about chemical modification in a lead. That is the first thing they always try to do. I can draw an analogy here. Looking at this picture, you see that the predator is here and a prey is here. So, predator has been understood or identified, the prey has also been identified. But since its beak is not so large, its accuracy is not, its tools which it requires to hit upon a prey are not adequate. One needs to do certain chemical modification, certain modification in the structure of a predator, so that it is able to actually hit upon or chance upon the prey, right. Disease is almost similar to that. So, your target lies here and your drug molecule is sitting here. You know that you have a lead. So, the lead is good, you know it is only going to hit the target, but it is still not apt enough, it is still not ready enough to hit the target. So, you do certain chemical modifications, make it really efficacious, make it almost side effect free, and then that is how you modify and generate a drug molecule. So, that is how we find a lead compound first, and that is followed by molecular modifications, and that brings about a drug molecule in the market. Generally, what we do is certain simple chemical modifications. So, those simple chemical modifications are done to improve therapeutic properties or bring down the effect of or bring down the side effects, and those simple modification could be just add on a certain functionality. For example, an hydroxy group is being acylated, or let us say a double bond is being reduced, or let us say an ether is being introduced in an alcohol. So, similar type of structural modifications, right. I will explain this with a couple of case studies, and you would understand this concept of molecular modification better with these case studies. So, I will begin with a story of cocaine. Cocaine is a very effective local anesthetic molecule. Okay. It is generally, it had been obtained from nature from the leaves of Erythroxylon coca, which is a bush which is native to highlands of South American Andes. And then when people realized it was a wonderful anesthetic, by then people also understood that cocaine produces disturbing effects on the central nervous system, ranging from initial euphoria to severe depression, and not to mention that people who are fed on cocaine, they become addictive on this molecule also, which means that there are sizable side effects in addition to the kind of therapeutic effect which we are looking at, which is an anesthetic effect, right. So, then the solution lies in molecular modification of this natural occurring lead. So, cocaine is a lead here, and let us see how we bring about a chemical modification. So, then we realized that after certain period of time, the scientist felt that cocaine can actually be simplified to basically this type of an ester, which would have a terminal tertiary amine joined with that ester, and the side chain is almost similar of length as is being there in cocaine. So, with this lead compound we got an improved lead compound, right. We still not have reached the final target molecule. So, what we have done, we have cleaved the bicyclic system and we have removed a methoxycarbonyl system from this molecule. Now, what that leaves with us? So, what that leaves for us is the portion of the molecule that carries the local anesthetic activity, which is the pharmacophore, which we also called as the modified lead, and that can act as a drug without its damaging central nervous system effects. This people realized. So, when they modified this and they got this knowledge, they got an improved lead compound, which is an ester of benzoic acid, which I showed in the previous slide also. The alcohol component of this ester would have a terminal tertiary amine group, right, and then this would not really pass so easily through blood brain barrier and would not cause so many psychopathic reactions or those side effects which we spoke about, addictive side effects and all, right. So, based upon this knowledge, hundreds of esters were then synthesized, which resulted in esters with substituents on the aromatic ring, esters with an alkyl group bonded to the nitrogen, and esters with the length of the connecting alkyl chain modified. So, basically what we did, what people did was they changed the length of this ester, alkyl chain length of this ester. They also changed the alkyl portion of this amine, and they also tried to make certain changes in the aromatic ring and even also in that ester linkage. And the result was that three important drugs were discovered: benzocaine, novocaine and xylocaine. Benzocaine was generally for topical administration, which means used as a cream, whereas novocaine was a drug which was used for intravenous injections as one of the most widely used intravenous anesthetic, which was then replaced by a further better drug called xylocaine or lidocaine. And if you look at the structures, what changes have been brought here? Basically, in these two structures, if we see, both are administered as anesthetic within the body, and if you notice the changes, instead of an ester here, one has converted that ester into an amide. What is the impact of it? Esters are easily hydrolyzed, whereas amides are not, right. So, an ester would be quite amenable to hydrolytic enzymes inside the body, and that is why it is important it is only given intravenously, because if you take it as a pill, it is very likely that the molecule will be hydrolyzed, and otherwise also. So, its lifetime, its half life would be pretty short, right. Whereas, for this molecule, it is not easy to cleave this amide bond, and hence this molecule is not going to be eliminated so soon, and hence its half life would be more. This half life would be further prolonged by having these two methyl groups here, which are overhanging on this amide linkage, and also this alkyl chain on the nitrogen atom. So, your lidocaine, xylocaine in every possible comparison was certainly a better molecule than novocaine, and that is how drugs are synthesized and drugs are made. So, we started from a molecule which was nature driven, right, and from that which was cocaine, and from that nature driven molecule we accepted it as a lead compound, made certain modifications, simplified that molecule, and got hold of three very important structures and three very important drugs, right. Likewise, I am bringing about the second example, and this example is of morphine, again a nature derived compound which is obtained from opium, and it is a very widely used analgesic. In fact, it is a golden standard as far as analgesics are concerned, one of the most prominent pain relievers, okay, ever discovered. So, then since it is obtained naturally, it also contains around certain amount, this is the structure of morphine, and it also contains with it certain other related compounds, for example, codeine, and codeine is nothing but a methyl ether of this morphine. So, one of these hydroxy groups is being converted into an ether, and that gets you to codeine, which is less of an analgesic compound, but more of a cough suppressant. Okay. So, it profoundly inhibits cough reflexes, but the problem is it is also an addictive compound. So then scientists get together and they try to work upon these molecules, and what they did was they made certain modifications in this portion of the structure, in this portion of codeine. If you remember, there was a double bond here, there was an OH here, and there was an furan ring here. So all of this is removed, and that gave them a compound which is called dextromethopren, which has profoundly useful cough suppressant properties, but less side effects of the previous compound, of its precursor compound. So again, chemical modification has been done in order to get a better drug, right. Likewise, another hands-on this chemical modification on this molecule morphine gave you another compound here, but this compound, although it was found 2000 times more potent than morphine, but it was also extremely toxic and was not advised for humans, and generally it is used to tranquilize elephants and other large animals. Now, on one side I told you when you converted this OH into an ether. Another modification could have been done on these two etheric on these two hydroxy functions here, functionalities here, and that is one can acylate both these functionalities, and then if one does that, then morphine is converted into heroin. Remember, we started with heroin. I told you that heroin was more potent than morphine, but it also was able to reach to the brain better in comparison to morphine, and it is better because you have converted a more polar molecule into a more non-polar molecule. And always remember, more non-polar molecules, they enter the brain rather easily in comparison to polar molecules. Okay? So, once it reaches brain, facile or in a better way in comparison to morphine, it brings about the side effects which we heard about, which actually changed the image of heroin, right. So, somewhere down the line, some German chemists, they synthesized this molecule methadone for a different property, but they did not realize that this methadone actually has a basic scaffold, or what we called a pharmacophore of morphine. So, it can also be used for the same purpose. And then people realized that in contrast to morphine, methadone can be administered orally. So, with morphine, one of the major obstacles is it has to be given in an injection form, whereas this compound could be taken in the form of a pill. It had a considerably longer lifetime, half-life, which is 24 to 26 hours, and consequently it can be used to treat chronic pain and the withdrawal symptoms of heroin addicts, right. So, an important molecule. We also need to understand how it is similar to a heroin molecule or a morphine molecule, or for that matter all these morphines, codeines, methadone, and all these molecules have the same basic pharmacophore. Okay. But before we do that, I would tell you, even this methadone was further converted into a chiral compound, and here is this chiral center carbon here, and this chiral compound had shown in one of its isomeric, in one of its stereochemical form, it showed a better potency than methadone itself, right. So, I spoke about the basic pharmacophore in this case, and you would realize that in all these analgesics, the basic scaffold consisted of this aromatic ring. Adjacent to this aromatic ring was a quaternary carbon, and then 2 carbons after you would have a nitrogen which is joined to another 2 carbons. You look at any of these structures and you would realize whether it is this structure here or whether it was any of these structures here. You look at this molecule, there is this aromatic ring, then there is this carbon which is quaternary, and then 2 carbons more, and then it is joined to a nitrogen which is joined to 2 carbons, 1 carbon here and another carbon here, right. You go to this compound or any compound for that matter, and you would realize that this is the basic pharmacophore. So, what do we understand? In a nutshell, we realize that molecular modifications are actually the creators of drugs. So, for that you got to have a lead compound. In one case we saw that lead compound was cocaine, and from that cocaine we derived this improved lead compound, and this lead compound upon further chemical modification gave us three very important compounds: benzocaine, xylocaine and novocaine. In the second case, morphine was the lead compound. It gave us this pharmacophore, and based upon this pharmacophore we could get so many drugs: codeine or heroin or dextromethorphan or methadone or alpha acetyl methadone, right. So, we understood in this lecture how do we differentiate a drug from a medicine. That was number one. Then what are the properties of that drug molecule, how you would classify a drug molecule, right. That was number two. There was various modes of classification. Then also how a drug is going to impact or bring about its required effect, right. So, we discussed about the targets, we discussed about its dosing and all that. And finally, how do we actually synthesize drugs? So, how are the drugs made? So, with this we will continue in the next lecture topics related to drug targets. We will discuss drug targets in details. Then we will also discuss how those drugs actually interact with those targets, what is this concept of binding, what is this concept of receptor sites and all that stuff. And eventually I think the next lecture will pertain to only these 2 points, and then in the third lecture of this series we will discuss about applications of drugs in certain pathological conditions. So, I hope you would have an informative session with me. I thank you once again for all the time and staying with me. I look forward to your presence in the next lecture. Thank you very much.